pressure in a fluid, let's consider a situation where you've got some tank and it's full of some fluid, water or whatever. So this is all, whatever the substance is. This area is full of it. Okay. At the top, there's some pressure, right? There's atmospheric pressure. The force on the top, since pressure is force per area, the force at the top is atmospheric pressure times that area. Okay. At the bottom, the force acting on the bottom of the container is equal to that same amount of pressure, because if you push on the top of the fluid, it's going to transfer that push to the bottom as well. It's like, if I push down on this paper, there's a downward force on the paper, but then the paper also then exerts a downward force on the desk. Same sort of idea there. So there's that force, plus there's also the force from the weight of the fluid. This is mg for the fluid. Now let's say if this fluid has some density rho, brief letter rho, we know that density times volume equals mass. Therefore, we can say that the force at the bottom is atmospheric pressure times the area plus rho v g. All right. Now this volume, of course, just using geometry, the volume, I'm running out of space, I'll do this in the next line. We have pressure, atmosphere times A plus volume is just if this is a regularly shaped container, it's the area of the surface times the height of the container. So that volume becomes area times height times G. So that is the force at the bottom, which means that the pressure at the bottom, which is force divided by area, just cancels out that area. We have atmospheric pressure plus rho g h. And it turns out that this equation for pressure isn't dependent on what kind of container this is. So I kind of did this assuming that this volume was equal to area times height. Well, you can just as easily do an integral for that and come up with the same result, that regardless of how the thing is shaped, the pressure at the bottom is just rho g h. So if this is some height h, I could also have a container that was, all goofily shaped, something like this. And if that is full of fluid up to a height h, the pressure at the bottom will still be atmospheric pressure plus rho g h. Doesn't matter how this is shaped. It doesn't matter if our container is, has different cross-sectional areas as you go up. All that matters is the density of the fluid and that height or depth of the fluid, h. More generally, we can apply this to any 2 points. It doesn't have to be bottom and atmosphere. The difference in pressure between any 2 heights we can write as the second pressure is equal to the first pressure plus rho g h, where h is the height difference between the pressures, and we're assuming that P1 is the higher point. So any 2 points in a fluid, so from any point P1 to any point P2 that are separated by some height h, this is the pressure difference between these 2 points. So for example, let's say we have a submarine that is 20,000 leagues under the sea. 20,000 Leagues Under the Sea is the title of a film. Might be before your time. It's 7 meters from the top of of the sub to the bottom of the sub, what's the pressure difference between the two? Well, we can say that the pressure at the bottom is just equal to the pressure at the top plus rho g h. And this rho g h then is our pressure difference. And consulting the table in your book, on page 500, you should mark that page or keep it in mind, because we'll use that table a lot. It's a table of densities of different substances. Seawater has a density of 1025 kilograms per meter cubed. Right, okay. And then G is 9.8, and our height is 7. And so the pressure difference between the top and bottom is 1028 times 9.8 times 7, which is 70,315 pascals, or a lot of times, because of the ranges involved, pressure is given in kilopascals, as you read in your book. And a kilopascal, this is also in what you should have read in your book, but a pascal is a Newton per meter squared, which makes sense as pressure is a force per area. Now, if the same sub is submerged in an unknown substance, and the pressure difference between the top and the bottom is now 65 kilopascals. What is the density of that substance? Well, again, we can use that our change in pressure is rho GH, and therefore we can say 65,000 equals our unknown rho times 9.8 times 7, and punch that in. 65,000 divided by 9.8 divided by 7 comes out to 947.5. So a rho is about equal to 947.5. And rho is mass per volume, so that's kilograms per meter cubed. If we look at our chart, that looks like olive oil is 920, so maybe that's some kind of oil or something relatively similar to olive oil. So that's how we can use our pressure equation. The barometer is an instrument that measures pressure, and it does so using the same sort of principle. Usually for a barometer, mercury is used because it has a high density, and I'll explain why that's important in a minute. But any substance, in theory, can be used. It just might not be quite as practical. So basically what happens is that you have a tube of some kind, and you make it full or close to full with some substance, as I said, usually mercury, and then you flip it over so that it is inside of inside a little pan that is also full of this substance, whatever it may be. And then, the liquid in here flows down into the pan, but then it stops at some height. Now up here, inside the tube, nothing has had the opportunity to be in there. So this is a vacuum. So the pressure exerted on the top of this liquid here is 0. Outside of here, we have atmospheric pressure. And this fluid then doesn't flow down all the way into the tube. Let me draw a little bit more schematic sort of diagram, if I can. Yeah, let's draw it like this. So then there's liquid in this tube, and then there's liquid outside the tube, and they wind up being at different levels. Okay. Now, the way this liquid flows has to do with pressure. Okay. Basically, the pressure at equal heights must be equal. if things are going to be in equilibrium. Well, why is that? Well, if we had a pressure on this, out here, that was larger than the pressure at that same point in here, then there would be a net force on the liquid here, and it would flow up into this tube. Likewise, if there was greater pressure over here, or not up there, but at this point right here, if there was greater pressure inside the tube right here than there was outside the tube, then the liquid would tend to flow out because there would be a net force on it. So the pressure has to equalize, right? So the pressure out here is atmospheric pressure. If the liquid's up to here, here. Pressure out here has to be atmospheric pressure. The pressure at that same height inside is just equal to the weight of the fluid in here. So whatever height this is at, the pressure right there is just rho g h of the fluid. So we can determine, and those two have to be equal in order for the fluid to not flow. So we can use a barometer then to determine what the atmospheric pressure is at a given time and place. We do have a standard atmospheric pressure that we use. We say that's 101, about 101 kilopascals. Is typically used as the standard value of pressure, but pressure actually fluctuates a lot based on elevation and also based on weather. Usually the pressure will drop right before it rains. And pressure can be higher at different times, whatever. Actually, some people are very sensitive to this pressure change. Whenever it rains, I usually get a headache because then the internal pressure in your body, like the pressure going outward from inside your body, is different than the atmospheric pressure, and that creates a net force either inward or outward, depending on if the pressure changes suddenly outside. Your body will naturally establish equilibrium with the atmosphere. And if the pressure suddenly changes outside and your body hasn't had a chance to adjust yet, then that can create a net force, which can cause headaches. I tend to get headaches whenever it rains because the pressure drops, and then the pressure inside my body is different than the pressure outside my body. Anyway, and the reason that mercury is typically used is because mercury has a high value of density. And because its density is higher, as the pressure changes, the height doesn't change as much as it would if rho was lower. And so that enables us to make barometers relatively small, relatively smaller than they would be for another liquid. Of course, mercury has the downside of being poisonous. If it breaks, you don't want to get it on your skin and whatnot.